Welcome to Engineers Mindset. Now let's say we have the beam on the board and we are asked to do the shear force and bending moment analysis, determining the point of maximum bending moment and the point of contraflexure. Okay, so we have the beam on the board. First thing to do is always to outline the free body diagram. So we have F, B. So we bring back the beam. Okay, now we realize that at point B we have a pin support, and for a pin support we always have two reactions. One of the reactions is vertical and one is horizontal. So we simply have these two reactions at point B. So simply call this RBY and call this RBX. The reaction at point B, X and Y. This is point A. Also, we have a 600 kilonewton force at point C acting downwards. So we indicate that here, this is point C. We have 600 kilonewton force at that point. Okay. Also, we have at point D 600 kilonewton force. So this is point D. We also have 600 kilonewton force at point D. This is point D. At point E, we have a roller support, and for a roller support, we have just one reaction normal to the surface. So we have a roller support, just one reaction at point E. So simply call this REY. Then finally, we have point F. Okay. Now, point A is 2 meters from point B. So we have these 2 meters apart. Point B to C is actually 3 meters apart. 3 meters. Point C to D is 2 meters apart. We have 2 meters. Point D to E is 3 meters apart. Point E to F is 2 meters apart. But this beam actually carries a uniformly distributed load across the entire span of the beam, across the entire length of the beam. So there's a UDL across the entire length. And to convert the UDL to point load, simply multiply the value of the UDL to the length covered by the UDL. Since the length is across the entire portion of the beam, that means we are going to multiply the value of the UDL now, which is 150 kilonewtons per meter, to the total length of the beam. The total length of the beam is simply 2 plus 3, that's 5 plus 2, 7 plus 3, 10 plus 2, 12. So in this total length of the beam is 12 meters. And if you multiply 150 by 12, it gives us a point load due to what? This UDL. So to convert this UDL to point load, simply multiply 150 by 12. 150 by 12 is what?
1,800.
So 160 by 12 is 1,800. And if you're placing this load, you place it at the middle of the length carried by the beam. If 12 is the length, then middle of 12 is simply 12 divided by 2. That should be 6 meters apart from point A to point B. Okay, so from point A, we measure out 6 meters. From A to C is actually 5 meters, because this is 2 plus 1, that's 5. So 6 meters is actually what? Found at the middle of this C to D, because from C to D is 2 meters. So we can have our 6 meters at the middle. So simply from point A, from point A to where the load is found is actually what? 6 meters. So you have the load to be 1,800 kilonewtons. That becomes the point load of the UDL. So from point A to the point load is 6 meters. From the point load to point B to point F is also 6 meters. Okay, so you have the 6 meters. So total length is 6 plus 6, that's 12 meters. That's the first thing to do. Now, the reason why we converted this UDL to point load is just because we need to find what these reactions RBY and RBY. Okay, we need to find this reaction. So we need to first of all convert the UDL to point load. So after this, we can employ our equilibrium equation from equilibrium law, from static equilibrium. Okay, we have that summation first in the x-axis, summation f of x is equal to 0. So we put all the force pointing the x-axis as 0. And the only force we have on the x-axis here is simply RDX. So this simply implies that RDS is equal to 0. Okay, so we'll have that. Next is to employ the second equilibrium law, which is summation of force in vertical axis summation f of y equals 0. Let's consider vertically upward force as positive, vertically downward force as negative. Okay, so if that's the case, we'll now start to add all the forces from the system. So we have RBY pointing upward, so it's positive. Pick it up, RBY. Next we have 600 kilonewtons force acting downward, so it's negative, minus 600 kilonewtons. Next we have the 1800 kilonewtons force acting downward, negative, minus 1800. Next we have 600 kilonewtons force acting downward, so it's negative, minus 600. Okay, and finally we have REY pointing upward, so it's positive, plus REY, and this is equal to 0. Okay, so REY minus 600 minus 1800 minus 600 simply gives us minus 3000. So you have minus 3000 plus REY, and that's equal to 0. So let's simply send minus 3000 over to this side of the equation. Negative sign plus and equal sign becomes positive. We simply have that REY, okay, plus REY is now equal to 3000. So call this equation 1. So equation 1 contains two unknowns in one equation, which is very impossible to solve. So the only way we can make the grade for this is by simply taking moment about any point on the beam. But I said the best way to take moment is about the point where we have numerous of force on the beam. So we have about two forces at point B. So simply we take moment of force at point B. Alright, so take moment at point B. Take moment at point B. Summation of the entire moment at point B is equal to 0. Let's consider clockwise moment to have positive values and anti-clockwise to have negative values. Okay. So we take the moment of all the forces about point B. Moment of this force, 600 kilonewtons what about point B. The force is acting downward, so it will turn about in this direction. Move from this point to this point. So it turns in this direction, which is positive. That's clockwise. And the distance it takes this force to get to point B is simply what? 3 meters. So we simply have that between 600 multiplying by 3. Also, we have the 1800 kilonewtons force acting downwards. Since it's acting downwards, it will also turn about in this direction, all the way from this point to point B. And it's positive because it's clockwise. Distance it takes this force to get to point B. Remember, this is acting at the middle, so remember this force is acting at the middle, so it's actually 1 meter apart. It's 1 meter, and it's also 1 meter. Okay, so it becomes total distance take this force to get to point B is simply 1 plus 3, which is 4. So we simply have plus 1800 times 4. Okay, next is 600 kilonewtons force acting downwards. We also have a turning effect in this direction, which is positive. Distance it takes this force to get to point B is simply 1 plus 1, which is 2, plus 10, that's 5. So you simply have plus 600 times 5. Okay, finally, REY is pointing upwards. So the moment of this force goes in this direction. It turns all the way from point A down to point B in this manner, which is anti-clockwise. And the distance it takes this force to get to point B is simply 3 plus 2, which is 5, plus 3, that's 8. So you simply have minus REY multiplying by 8, and this is equal to 0. Okay, so we have this. Let's now expand the bracket. Okay, 600 times 3 is 1800 plus 1800 times 4. 7,200. Okay, plus 600 times 5. That's 3,000. Okay, minus 8 REY. And this is equal to 0. So we need to find out the evaluate 1800 plus 7,200 plus 3,000 and see what we're going to obtain. So So 1,800 plus 7,200 plus 3,000.
12,000.
Okay, yes, 12,000. So you have 12,000 minus minus 8REY. Okay, 12,000 minus 8REY, and this is equal to 0. So now we send minus 8REY over to this equation. Negative sign plus sign equal to sign equals positive. We simply have 12,000 equals 8REY. So to make REY subject, divide both sides by 8. Therefore, REY is simply 12,000 divided by 8. And so therefore, REY is equal to 12,000 divided by 8. We have 1,500 kilonewtons. This becomes the reaction at point E. It becomes the reaction at point E. Okay, so having known this reaction, we simply substitute into equation 1 to obtain RDY. So substitute that into equation 1. Equation 1 simply gives us RDY plus, in place of RDY, we simply put 1,500 equals 3,000. Okay, so to make RDY subject, simply send 1,500 over to this side of the equation. So we simply have 3,000 minus 1,500. So that simply implies that RDY itself is now equal to 1,500 kilonewtons. So we obtain the two reactions, and I said since you're dealing with a UDL, you plug back the two reactions into the original beam, because for us to be able to do shear force and bending moment analysis or find the point of maximum bending moment and the point of contraflexure, we need to form what is called the shear force equation, and that is only obtainable when we took section. So we have to take section about the points on the beam due to this UDL. So for that reason, you put back the reactions into the original beam. Okay, let's do that now and see. So for the pin support, we already have the reaction, and we obtain the value of the reaction as 1,500. So we have it at 1,500 kilonewtons. Okay. Also, we also obtain the same reaction for the roller, 1,500. So we replace it. Is 1,500 kilonewtons. Okay. Alright, so we can start our shear force analysis now. So I simply said shear force is simply the stepwise summation of the entire force acting on the system or on the beam. From beginning of the beam, at each point of the beam to the end of the beam, we consider upward forces as positive and downward forces as negative. So we start from the beginning at each point and keep adding all the forces till we get to the end of the beam. And at the end of every shear force analysis, we must always obtain 0 as the answer. Okay, so shear force at point A simply means the force that exists at point A. And if you take a look at point A, there is no force at point A. So it means shear force at point A is simply equal to 0. There is no force at point A, therefore the force is 0. Now, between A to B, there is a UDL. Because of this UDL, we have to form what is called shear force equation. And to do that, we have to take what is called section. So we consider a section. We consider a section XX. Okay, consider a section XX at a distance of x from A to the point of section. Alright, so from point A, let's consider a section XX. Okay, consider a section XX. And we are saying distance from point A to the point of section is simply what? X meters. Let this be the distance from point A to the point of section, x meters. If that's the case, then it means now that the length of the UDL about the point of section, that's from the point A to the point of section, the length of the UDL about that point is simply what? X. And remember, to convert the UDL to the point node, all you need to do is simply multiply the value of the UDL to the what? Length covered. If the new length now is x, that's the length of this UDL about the point of section. If the length is x, then it means to convert this UDL to a point node, it becomes shear force along AB, because we are taking section now somewhere x is along A to B. So this becomes shear force along AB, and that's simply equal to, okay, the length of the UDL now. The last shear force we had is the 0, so bring it out 0, okay, minus the length of the UDL about the point of section is x meters. So therefore, to convert this portion of the UDL about the point of section to point where we simply multiply the load intensity, which is 150 by simply x. X is now the length of the UDL about the point of section. Okay, so at point B, x is now equal to a length from point A down to point B. Once this value runs from point A down to point B, x is now equal to 2 meters, because from point A to B is actually 2 meters. So at B, x is equal to 2 meters. So this now means that shear force at point B is now equal to, okay, we have 0 minus 150 times 2. Okay, and this is simply what? 0 minus 300. Therefore, shear force at point B is equal to minus 300 kilonewtons. Okay, so we call this shear force D prime. Okay, so we can call it shear force D prime, which means initially at point B, because a closed loop at point B shows that there's a reaction, a vertical reaction at point B, and that reaction is what? 1500. So this was the initial value of the shear force, as this particular force 0 kilonewtons moves along AB down to point B. The initial value gave us 1000, so it gave us 300 kilonewtons. Therefore, finally at point B, we simply represent that with shear force B prime prime, showing finally at point B, this force now minus 300 kilonewtons now encounters an upward force of 1800 kilonewtons. Since it's upward, it's going to be positive, so we simply have plus 1500 kilonewtons. Okay. Alright, so this will actually give us 1200 kilonewtons. So it means the shear force at point B is equal to 1200 kilonewtons. Now this force now moves somewhere along B to C. This same force, 1200 kilonewtons. So simply call shear force BC. So break down the force, 1200 kilonewtons. Now moving along BC, it now encounters a UDL from point B down to point C. So because of this UDL, we have to take section. Since there's a UDL on the beam, that means we have to continuously take section from the beginning of the beam to the end, because of that UDL from beginning to the end. So we take section, okay? So we consider a section XX at a distance of x from point A, now along BC. So along BC, you are considering a section, and you say distance from point A to the point of section remains x meters. So from point A to the point of section, you are calling that distance was x meters. Okay. Now we need to now find the length of the UDL between point B to the point of section, because this is shear force and not bending moment. In bending moment analysis, after you're done with one joint, let's say we're done with point A and move to point B, we still have to consider all the forces behind point B to take moment about point B. If we move down to point C, we have to consider the forces behind point C from A to B down to point C. But in shear force, it's actually stepwise at each joint. So after point A, we move to point B. After point B now, we are going to point C. So we need to find the length of the UDL between point B to the point of section now. We are simply saying from A to this point of section is x meters. Okay, so what's now the distance from point B to the point of section? To find this, you simply will take away the length that you don't need, the distance you don't need from that point A, or from where x runs from point A. Take away that distance you don't need from x. If from A to the point of section is simply what x meters, then distance from point B to the point of section is simply from where to this point is simply take away these 2 meters that we don't need from what x. So that distance simply gives us x minus 2. That becomes the distance from point B to the point of section. This distance now is now the length of the UDL between B and the point of section. Okay, so to convert that UDL to point, we simply multiply the density of the UDL by what? The length. The length now is x minus 2. So we simply have, okay, 1200 minus value of UDL is simply 1000 simply 150 times x minus 2. This becomes the point load of the UDL. Okay. Now, when x finally runs to point C, x is now equal to total length from point A now to point C. And from point A to point C is given at least 2 meters, this is 3 meters. So from A to C is actually 5 meters. So at C, x equals 5 meters. Therefore, shear force at point C is now equal to 1,200, okay, minus 150 into, in place of x, you simply put 5 minus 2, okay? And this is equal to 1,200 minus 5, 150 into 5 minus 2 is 3. And this is equal to 1,200 minus 150 times 3 is 450. So 1,200 minus 450. This simply implies shear force at C. Okay. 1,200 minus 450. So you have 750 kilonewtons. So as always, you can also call this shear force C prime, which means initially at point C, because at point C, you notice that there's a downward force of 600 kilonewtons, so you cannot neglect it. So this was the initial shear force due to the 1,200 kilonewtons was moving along BC. So we call this initially at point C, shear force C prime is equal to 750. But at point C, there's a 600 kilonewtons was acting downward. So we now consider that shear force C prime, which means finally at point C, this 750 kilonewtons force now encounters a 600 kilonewtons force acting downward. So you simply have minus 600. So 750 minus 600 simply gives us 150 kilonewtons. So that's the final shear force at point C, 150 kilonewtons. So therefore, moving now along CD, this shear force along CD, this 150 kilonewtons force that we have last, you bring it down 150. This force now encounters the UDL also along CD, because there's also a UDL from C to D. So because of that UDL, you also take section. Okay, so you take section, consider a section XX at a distance X from point A along CD. So it's now going to be along CD. So you consider a section here. Okay, X, let the distance from point A to the point of section. Okay, simply do what? X meters. Okay, distance is X meters from point A to the point of section. Now, if the distance is X meters, what is now the length from point C to the point of section? What is now the length of the UDL between point C and the point of section? So I simply said to get this length, simply remove the other length you don't need. I don't need 3 meters now, I don't need 2 meters. I'm moving from C, so which means I don't need all these lengths behind. Simply take away these 2 lengths from what? X. And 3 plus 2 is 5. So we need the length from point C to the point of section is simply X minus 5. That is the length of the UDL about the point of section. So if that's the case, then shear force C is equal to 150, which was the final shear force we had, minus, to convert the UDL to point load, multiply the UDL intensity to the length over. Intensity against 150, length now is X minus 5. So you simply have 150 times X minus 5. Okay, so at D, at point D finally, X is now equal to total length from point A to point D, and total length from point A to point D is actually 2 plus 3, that's 5, plus 2, that's 7. So at D, X is equal to 7. So it means shear force at D is now equal, so we have 150 minus 150 into 7 minus 5. This is equal to 150 minus 150 into 7 minus 5 is 2. So this is equal to 150 minus 150 times 2 is 300. Okay, so shear force D. Okay, so all the shear force D prime is equal to minus 150 kilonewtons. So all that one shear force D prime, because that's the initial shear force at point D, because at point D we also encounter the downward force of 600 kN. So initially at point D, the shear force is simply minus 150 kN. So we call that shear force D prime. Finally at point D, shear force D prime prime, this 150 kN force minus 150 now encounters a downward force of 600 kN. So our since now becomes minus 600, and the value is simply equal to minus 750 kilonewtons. So now this minus 750 kilonewtons force now moves along DE. So we have shear force DE. This minus 750 kilonewtons force moves and now encounters a UDL along DE. So as usual, we take a section somewhere around along DE. So take a section. Okay, so consider the section XX at the distance x from A along DE. So distance from A to the point of section is simply what? X meters. So we simply consider from A to the point of section now, call that distance x meters. It remains x meters. So if that is distance, then what is now the length from D? So what is now the length from D to the point of section? Okay. If from A to the point of section is x, distance is x meters. So what's now the length from D to the point of section? That gives us the length of the UDL about that point. That gives us the length of the UDL about that point. Okay, so I simply said, to get this length, simply take away the other lengths and you don't need. So notice that this is 2 meters, this is 3 meters, that's 5, and this is 2 meters, that's 7. So it means move 7 from what x. That gives you the length of the UDL from point D to the point of section. So that length is simply x minus 7. Okay, so this is now the length from D to the point of section. Therefore, shear force D is equal to minus 750 minus 150 into, to convert the UDL to point to multiply by the length, which is x minus 7. Okay. Now at E, x becomes the total length of the entire beam from A to E. So from A to point E. Okay, so from E, you have 3 plus 2, 5 plus 3, 8. 8 plus 2 is 10. So at E, x equals 10. Therefore, shear force at E is equal to minus 750, okay, minus 150 into, in place of x, I will simply have 10 minus 7. And this is equal to minus 750 minus 150 into 10 minus 7 is simply 3. That's minus 750 minus 450. 150 times 3 gives us 450. Therefore, shear force E prime, all this, we simply call this E prime, which means initial shear force at point E. We simply call it E prime, that's shear force initially at point E. That's equal, it gives us minus 750 minus 450. That should be minus 1,200 kilonewtons. So that's the initial shear force at point E. Okay, so notice now that at point E, we have an upward force of 1,500 kilonewtons. At point E, there was an upward force of 1,500. So simply shear force E prime prime, which means finally at point E, shear force E prime prime simply gives us minus 1,200 plus what we have here, which is 1,500. Therefore, shear force E prime prime is simply equal to 300 kilonewtons. Okay, so this shear force moves from point E down to point F. But moving along F, it encounters a UDL between E to F. So because of this UDL, as always, we'll consider taking a section. So we take a section, consider section XX at a distance x from A, now it's along EF. Distance from point A to the point of section still remains x, so from point A, now to this point of section is simply what x. Okay, if that's the case, then what is now the length of the UDL from point E to the point of section? What is now the length of the UDL? So I simply said, since from A to the point of section is x meters, then take away the other length you run from x. That will be the length of the UDL from point E to the point of section. Okay, so at this moment, we don't need 2 meters, 3 meters, plus 2, 5, plus 10, 8, plus 2, 10. So we simply take away 10 from x. And we simply have, okay, we simply have the distance of the UDL from point E to the point of section. From this point, so we simply x minus x minus 10. So that gives us the length of the UDL at the point of section. Okay, so I will actually need the shear force values. So let me just pick it up somewhere here so I can make space for myself on the board. So shear force A, let me do that. Shear force A actually gives us 0. And alright, so shear force B prime, which shows us shear force at point B, give us here to be 1,200 kilonewtons. 1,200 kilonewtons. Alright, so I can wipe that and make space for myself on the board. Okay. Alright, so shear force along EF is not equal. So the final shear force we have, which is 300 kilonewtons, this force moved and now encounter a UDL, and the length of the UDL is simply x minus 10. So to convert that UDL to point, to simply multiply 150, which is the intensity of the shear force of the UDL, multiplied by the length, and length is simply x minus 10. Now at F, x becomes total length from point A to F, which is simply from A to F, and that's simply 2 plus 3, 5 plus 2, 7 plus 3, 10 plus 2, 12. So x equals 12 meters. Therefore, shear force at point F is now equal to, we have 300 minus 150 into x is simply 12. So you have 12 minus 10. Okay. This is now equal to 300 minus 150 into 12 minus 10 is 2, and this is 300 minus 300, and that's equals 0. So at the end of every shear force analysis, we must always obtain 0 as the answer. Alright guys, so this is what I will do. I will simply plot the shear force diagram first before I go into the bending moment analysis, so I can have space to do the bending moment analysis. Okay, so to create space for myself, let's get down all the shear forces at one point. Let's get all the shear forces at one point to make a space. Okay. Let me get the shear forces at one point. I had shear force at A to be 0. So SFA equals 0. I had shear force at B. Please, we're using the double prime. That shows the final shear force. So that's what we use. Shear force B prime actually shows us shear force at point B. So we have shear force B is equal to 1,200 kilonewtons. Okay. Shear force C. Shear force C prime. We use C prime for C. Okay, this shear force C prime. And that's equal to 150 kilonewtons. That's shear force C equals 150 kilonewtons. Okay. Shear force D prime. We use shear force D prime for D. So that's shear force D prime, which is this, minus 750 kilonewtons. That's shear force D -750 kilonewtons. And finally, okay, shear force E prime. Shear force E prime will obtain 300 kilonewtons. That should be shear force E. So shear force E equals 300 kilonewtons. Then finally, shear force F. Finally, shear force F is 0. So shear force F equals 0. So I can write this side and use this for the diagram. Alright, so to plot the diagram, we still bring back the beam. So let's get the beam back. Okay. Okay, so we'll get back the beam the way it is. The reaction at point, this is point A, we obtain the reaction at point B, and the value is simply 1,500 kilonewtons. And also at point C, we have a 600 kilonewtons force. So this is point C, about 600 kilonewtons. We have a reaction at point D. We have a reaction at point E, still 1,500 kilonewtons. 1,500 kilonewtons. And we have a downward force at point D. Value is also 600 kilonewtons. So what we'll do is this: trace down all the points. This point B, this point C, this point D, this is point E, this point F. So to draw the shear force diagram, we trace down each of these points. Trace down point B, trace down point C, trace down point D, trace down point E, and trace down point F. Okay, so after doing this, you now look at your shear force values. Look at your shear force values, pick out the highest from the lowest. Also pick out those that are positive and those that are negative. So we have 1,200 highest, followed by 150, okay, followed by 300, followed by 150. Then we have just one negative sign, which is -750. So 1,200 is the highest, so it comes first, 1,200 kilonewtons, followed by 300 kilonewtons, so call that 300 kilonewtons, followed by 150, so call that 150 kilonewtons. Okay, then we'll have the origin, this should be the origin, O. So everything or every values above the origin is positive. Every value below the origin is negative, and the only negative value we have here is -750 kilonewtons. Shear force at D. So we simply have -750 kilonewtons. So trace out all these shear force values. Trace them all out. Trace them all out. Trace them all out. Trace them all out. Alright, so we have this. We can now start to plot our shear force diagram. Shear force at point A, we obtain the shear force at A as 0. So simply shear force at A is 0. This is the 0 mark. This is line A. You simply asterisk. We obtain the shear force at B as 1,200 kilonewtons. Okay, that's shear force B prime. This is line B. This is 1,200 kilonewtons. So this is where they meet. You simply asterisk the points where they meet. We obtain shear force at C to be 150 kilonewtons. Okay, this is line C. This is 150 kilonewtons. This is where they meet. You simply asterisk. Okay, so this is line C. This is 150 kilonewtons, so this is where they meet, asterisk. Okay, the next is shear force at point D. Shear force at point D was minus 750 kilonewtons. This is line B. This is minus 750 kilonewtons. This is where they meet, so you simply asterisk. To obtain shear force at point E, shear force at E is 300 kilonewtons. This is line E. This is 300 kilonewtons. This is where they meet, so you simply asterisk. Okay. Finally, shear force at F is 0. This is line F. This is 0 mark. Asterisk. Now, since the beam carries a UDL from beginning to the end, it means we have to draw a shear force in terms of a UDL. And I said in the first series on shear force and bending moment analysis, please do well to look at the first video. I said that the shear force diagram for a UDL is simply a slant line. Since we have a UDL from point A to point B, you simply have a slant line connecting them together. So from point A, we have the first shear force is 0, so we simply connect with the slant line. We have this. Also, between B and C, there is also a UDL. So because of that UDL, you have a slant line connecting. You have a slant line connecting point B to point C. That's the shear force diagram for a UDL. Also, between C and D, you also have a UDL. So you connect with a slant line. Shear force diagram for UDL, you have this. Between D and E, you also have a UDL. So connect with a slant line, connecting D and E. Also, between E and F is a UDL, so you connect with the slant line. So this gives you the shear force diagram. So you can choose to shade the diagram if you want. So you choose to shade. Okay. Alright, so this gives you the shear force diagram for that analysis. Shear force. Alright guys, so we can start the bending moment analysis. After the bending moment analysis, we can draw the diagram. But today, to be clear, have it in mind that shear force, the point of maximum bending moment is the point where shear force changes sign from positive to negative. And if you look at this beam now, shear force changes sign first from positive, here this is positive and this is negative. So it means maximum bending moment will occur between point C and point D. This is where shear force changes sign from positive to negative. That is where maximum bending moment will occur. So to find the maximum bending moment, we will look for the shear force equation between point C and point D and equate it to 0. So we are going to do that now before we go into the bending moment analysis. Okay. Alright, so we are also asked to find the point of maximum bending moment. Okay, so I said the point where shear force changes sign from positive to negative is the point of maximum bending moment. And since shear force changes sign from positive to negative between point C and point D, it means the maximum bending moment occurred at this point between point C and point D. So all we need to do is to simply pick out the shear force equation between C to D and equate it to 0. Okay, so consider shear force between CD. Let's get the shear force equation between CD. The shear force equation between CD is simply 150 minus 150 into x minus 5. So you simply have 150 minus 150 into x minus 5. This is the shear force equation along CD, and that is where bending moment is maximum. Now, at maximum bending moment, max, okay, the shear force along CD is actually equal to 0. So which means in place of this, we simply replace 0. That simply means 150 minus 150 into x minus 5 equals 0. So let's simply say minus 150 into x minus 5 over to the cell equation. We now have 150 equals 150 into x minus 5. Of course, negative sign plus and equal sign becomes positive. Now, this is what I will do. Instead of expanding this bracket with 150, let me simply divide both sides by 150 so that 150 will cancel out. I will simply have 150 all over 150 equals 150 into x minus 5 all over 150. So 150 cancels 150. This goes into this, gives me 1. Okay. Alright, so I will simply have that 1 is now equal to simply x minus 5. So simply send minus 5 over to this side of the equation. Negative plus and equal sign becomes positive. That simply implies that x itself is now 1 plus 5, and therefore x is equal to 6 meters. So 6 meters is actually the point of maximum bending moment. X equal to 6 meters is the point of maximum bending moment. Alright, so we can now start the bending moment analysis. Bending moment analysis. Okay. Now, as always, from every run law, the moment of force about every point is 0. So the moment of force about point A is completely 0. So bending moment at A is equal to 0. Now, the way moment work is that we always take moment from the beginning of the beam to the end. So even after we move past one point, if we are gotten to point B, we have to take moment from point A down to point B. If we move to point C, we have to take moment of forces at point A and B down to point C. It continues like that from the beginning to the end of the beam. Okay? This is point B. So moment at A is 0. Now, moving along A to B, there is a UDL. So because of this UDL, I've always said, because of UDL, you always take a section to form now the moment equation. So we consider a section XX at a distance x meters from A along AB. So distance from A along AB, this section XX, and we're simply saying from A to the point of section is simply what? X meters. So this becomes the length of the UDL about the point of section. Now, what is the moment along AB? This is now equal to simply, since we don't have any force at point A, we simply take the moment of the UDL about the section. To convert the UDL first of all to point B, remember, simply multiply the intensity of the UDL, which is 150 by what? X, now the length. But this is now a point load and not moment. After we converted this UDL to point B, remember, let's say from here is A, this is from A to the point of section X. After converting this UDL to point B, we simply say, place it at the middle of the length. If the length from point A to this point is X, and this is the point load now 150 times X, then we simply say place it at the middle of the length. Middle of the length is simply X all over 2 and X all over 2. So which means the moment of this force, 150x about the point of section is simply 150 times what? X all over 2. So it doesn't end there. The distance now to the point of section becomes multiplied by X all over 2. So you have this. Now at point B, X itself is equal to total distance from A to B, and that was given as 2 meters. So from A to B is simply 2 meters. X is equal to 2 meters. Therefore, moment at point B is now equal to 150 times 2 all over 2. And this will simply give us 300 kilonewtons meter. So we have this to be the moment about point B. Okay, so moving beyond that point, we now consider moving along what BC. So because there's also a UDL along BC, it also prompts us to take section about that point. So we consider taking section at a distance x from point A along BC. So you take section along BC, xx, then the distance from point A to the point of section is x meters. So if you have this, now in bending moment, in Shear Force analysis, we found the length of the UDL between point B to the point of section, but it doesn't work so with bending moment simply because when taking moment, after you move past the point, you consider all the force behind and take moment of those force about the new point. So since from point A to the point of section, I still have the UDL running from point A to the point of section, I have to now consider what the moment of that force, or the UDL force, from point A about the point of section. That's the first thing. Secondly, now I have a force of 1,500 pointing upwards at point B. It is now this force that I will have to do for the length because this is just a point load, it's not a UDL. So I need to find the length of this force about what? A point of section. So as usual, if from A to the point of section is S, what is now from B to the point of section? Simply remove the length that we don't need out of it. So our length done there simply was 2 meters. So therefore the length of this force, 1,500 about the point of section, is simply what? X minus 2. Alright, so moment along BC is now equal to, first we have the moment of this force 1,500 kilonewtons. Since it's pointing upwards, let's consider the moment as positive. So we have 1,500 times distance it takes to get to the point of section, which is x minus 2. And then the moment of the UDL load now, the UDL load, first of all, to convert it to a point load, still remains minus 150 times x. This becomes the point load. Then you have to place it at the middle of this length, so it becomes x all over 2. This becomes the moment. So at C, x is equal to the total length from A to C, which is from this point to this point, and that's 3 plus 2, which is 5 meters. X equals 5. Therefore, moment at point C is equal to 1,500 into 5 minus 2 minus 150 times 5 times 5 all over 2. Okay, this is equal to 1,500 into 3. 5 minus 2 is 3 minus 150 into, okay, 150 times 5 times 5 over 2 is 2.5. So this is equal to 1,500 times 3 is 4,500 minus 150 times 5 times 2.5. 1875. So 4,500 minus 1875. Simply 2625 kilonewtons meter. That becomes the moment at point C. Okay. Now between point C and point D, there's also a UDL. Now we also have to take a section along that point. So consider a section XX at a distance x from point A, now along CD. So you simply take a section XX, distance from point A to the point of section is simply what x. You have this to the x, okay? If that's the case, now because of these two loads, 1,500 kilonewtons load and a 600 kilonewtons load on top of this beam, we need to now find distance of this load about point A. The distance of this load about point A, the 1,500 kilonewtons about point A, is still what we're looking for distance from point B to the point of section. So which means we don't leave this distance behind, which is 2 meters. So take away 2 meters from x. So if distance remains x minus 2. The distance of this load now about the point of section is simply, we are now interested from point C down to the point of section, which means we don't leave these other distances behind. And distance behind is 3 plus 2, which is 5. So simply take away 5 from x. That will give us the length of this load from point C to the point of section, which is simply x minus 5. We have that. Okay. So the moment of forces along, this is now moment along C. Along CD, it's now moment along CD, it's now going to be equal to, first of all, the moment of this 1,500 kilonewtons was about that point, simply this was 1,500 times distance it takes, which is x minus 2. Okay, next, if the 600 kilonewtons was about that point, we have minus 600, since it's pointing downward, let the moment be negative, minus 600 into x minus 5. And then, since from point A to the point of section that's the UDL, we also have to convert the moment of the UDL about the point of section. Okay, first of all, we convert the UDL to point load minus 150 times x. Okay, then we place that the length of the length, which is simply x all over 2. So that becomes the Shear Force equation along C. Okay, so at D, x is actually equal to total length from point A to point D, from point A down to point D, and that's simply 2 plus 3, 5 plus 2, 7 plus 3, 10. Right? No, 7 meters.
7.
So 2 plus 35 plus 2, 7. Total length from A to B is 7 meters. So x equals 7. So moment at point D is now equal to 1,500 in place of x should be 7 minus 2 minus 600 into 7 minus 5. Okay, minus 150 multiply 7 all over 2. You have this. So this is equal to 1,500 into 7 minus 2 gives us 5 minus 600 into 7 minus 5 gives us 2 minus 1,500 times 7 divided by 2 gives us 3.5. 3.5, so you have this. Okay, so moment at B is equal to 1,500 times 5. 7,500. Okay, minus 600 times 2 is 1,200. Minus 1,500 times 7 times 3.5.
That is 150.
Sorry, 150. So please take note, this is actually 150, not that, that's 1,500, sorry. 150. 150 times 7 times 3.5.
3675.
13675. Okay. So 7,500 minus 1,200 minus 3675. Seven five zero zero minus 1,200 minus 3675. All right. So moment at B is actually 2625 kilonewtons meter. Okay. Okay. So same thing. Now we move between D along D to E. So since we are moving along D to E, we also consider a section XX at a distance of x from point A along DE. So take a section there. XX distance from point A to the point of section simply call it what it still remains x meters. Is that the case? Then the distance of this 1,500 force about the point of section still remains x minus 2. Distance of this 600 kilonewtons force acting here about the point of section now still remains x minus 5. Now, we need to find the distance of this 600 kilonewtons force about the point of section simply from this point to this point. Okay, so I simply said the distances you don't need to take it off from x. That is the distance of each force to the point of section. Alright, so since we are point D, it means you don't need distance behind. This is 2, this is 3, that's 5 plus 2, 7. So you need this length x minus 7. That becomes the length of the UDL about the point of section. Due to what the length of this loop about the point of section. So therefore, moment along DE now is now equal to start with this first force 1,500 kilonewtons times distance x minus 2. We have 1,500 times x minus 2 minus 600 minus because 600 is going to now loss. So minus 600 times x minus 5 times x minus 5. Okay, next is minus 600 times x minus 7 minus 600 times x minus 7. Also, okay, and then to take the moment of the UDL from point A to the point of section, the length is x. So the moment of the UDL is simply just converting the point where we have 150 times x. Then multiply by a middle of the length, which is x all over 2. So you have this. Now at E, x becomes total length from point A to point E. So from point A to point E, total length is simply 10. From A to E, total length is 10. So x equals 10. Therefore, moment at point E equals, you have 1,500 into 10 minus 2 minus 600 into 10 minus 5 minus 600 into 10 minus 7 minus 150 multiplies, in place of x you have 10 multiplies 10 all over 2. This is equal to 1500 into 10 minus 2 is 8, minus 600 into 10 minus 5 is 5, minus 600 into 10 minus 7 is 3, okay, minus 150 by 10 divided by 2 is 5. So this is equal to 1500 by 8. 12000 minus 600 times 5 is 3000 minus 600 times 3 is 1800 minus 150 times 10 is 1500 times 5 should be 7500. Let's check. 150 times 10 times 5.
Okay.
7500. So the moment at point E is now equal to 12,000 minus 3,000 plus 9,000 minus 1,800 minus 7,500 minus 300 kilonewtons meters. So you have that. That's the moment at point E. So finally, we are at point F now. Okay. We are at point F now. So guys, let's just put down the values for moment at point A. So I will mix this. Moment at A is 0. Moment at A equals 0. Moment at B is 3,000 kilonewton. Moment at B equals 3,000. 300. Okay, 300 kilonewton. Alright, so this find out. So we are finally at the end. So also consider taking section at a distance xs. Consider a section xs at a distance of x from A along EF now. So somewhere around there, take a section. Let the distance from point A to the point of section still remain as of x. So the distance of this 1500 kilonewtons was about that point still remains x minus 2. Distance of the 600 kilonewtons force still remains x minus 5. Distance of this other force still remains x minus 7. We now need to find distance of this force 1500 about that point. So from this distance, from this point to the point of section, what is the distance? Simply take away the distances you don't need. We don't need 3. We don't need 2, that's 5. We don't need 3, that's 8. We don't need 2, that's 10. So it's simply x minus 10. That becomes the distance of this force about the point of section. So moment along EF is now equal to, okay, let's start with this force. 1500 multiplies x minus 2. Next, minus 600 multiplies x minus 5. Okay, next, minus 600 multiplies x minus 7. Okay, now this force is upward, so consider it positive. Plus 1500 multiplies x minus 10. And finally, the moment of the UDL, because UDL runs from point A to the point of section, so you simply have minus 150 times x all over 2. So you have this. Now at F, x is equal to 12, which is the entire length of the beam. Therefore, moment at point F is equal to 1500 times, in place of x you have 12 minus 2. Okay, minus 600 into, in place of x equals 12 minus 5. Minus 600 into, in place of x you have 12 minus 7. Okay, plus 1500 into, in place of x you have 12 minus 10 minus 150 by 12 all over 2. This is now equal to 1500 into 12 minus 2 is 10 minus 600 into 12 minus 5 is 7, minus 600 into 12 minus 7 is 5, minus plus 1500 into 12 minus 10 is 2, plus, okay, minus 150 multiplied by 12 multiplied by 12 divided by 2 is 6. You have this. This is 7. So moment at F is now equal to 1500 times 10 gives us 15,000. 1, 2, 3, okay. And then we'll have 600 times 7.
600 times 7, 4,200.
That's minus 4,200. Okay. 600 times 5 gives us 3,000. Minus 3,000. Okay. Plus 1,500 times 2 is simply plus 3,000. Okay. And then we have 150 by 12 by 6. 150 times 12 times 6.
108.
Minus 10800. So moment at F is equal to, okay. So let's add the positive values together. This is 1,000, this is 15,000 plus 3,000. That simply gives us 18,000. You have 18,000, and let's add negative values together. This is minus 4,200 minus 3,000, that's minus 7,200 minus 10,800. Minus 4,200 minus 3,000 is minus 7,200 minus 10,000 gives you minus 18,000, and this value is equal to 0. So again, at the end of every bending moment analysis, you must always obtain 0 as the answer. Okay? So we can now plot the diagram and possibly draw, find the point of contraflexure. Okay? So let's draw the diagram now and see. You can use this other diagram. I think I can wipe here. Yes, there's no value here, so I can wipe here. Alright, so as usual, place all the points down. So this is point A, place point A down, place point B down, place point C down, this is point C, place point D, this is point D, place point E down, this is point E, and finally point F, which is here. Okay, so we'll go through the moment analysis. Pick out our highest value from our lowest values. Moment at A gave us 0. Moment at B gave us 300 kilonewtons. Moment at C
2625.
gave us 2625. Okay. Moment at D 2625. Okay. Moment at E is minus, so 2625 actually happens to be the highest. So let's pick that value here, 2625. Okay. 2625, that happens to be the highest bending moment value. Followed by, we have 300 kilonewtons. That's moment at B.
265 is twice.
Yeah?
265 is twice.
You have to put it once. You can't write twice. Just in the once. Followed by B, moment at B is 300 kilonewtons, so we have 300 kilonewtons. Kilonewtons meter. Next moment we have moment at B is 265, moment at E gave us minus 300. So it means this is now our origin. Okay, so O. Everything above the origin is positive, so that's why I have 265 and 300 are all positive values. Below the origin are negative values, so this is minus 300 negative values. So and the moment at F is 0. So trace out these points. Trace out these points. Trace out these points. Trace out these points. Alright. So moment at A is 0. This is line A. This is 0. So you asterisk. Moment at B give us 300 kilonewtons. This is line B. This is 300 kilonewtons. So you asterisk. Moment at C give us 2625. Moment at C give us 2625. This is line C. This is 2625 asterisk. Moment at D also give us 2625. This is D. This is line D. This is 265. Simply asterisk. Moment at E give us minus 300 kilonewtons here. So simply asterisk. This is line E. This is minus 300 kilonewtons. So simply asterisk. And you have this. Moment at F is simply 0. This is line F. This is 0. You simply asterisk. So we have this. Okay. So, like I said from the introduction video in Shear Force and Bending moment analysis, please do well to watch all the Shear Force and Bending moment series for proper understanding. I said the moment diagram for a UDL is simply what? A curve. The moment diagram for a UDL is simply a curve. So we simply join this with a curve. We move from point A to point B, and then from point B to point C. This maintains to point D. Okay. And then down to point C, down to point E. Okay. And then down to point F. Alright, so this is your bending moment diagram. You may wish to shade if you want to, but that's your bending moment diagram. So bending moment, BMD, bending moment diagram. Okay. Alright, so the next thing that I was saying in the question is to determine the point of contraflexure. We have found the point of maximum bending moment. Now we need to find the point of contraflexure.